the covariance. And this is called the variance. So this denominator is called the variance because it measures how much x varies. All right. So suppose I gave you numbers. Suppose that x, suppose that all the xi were equal to a constant. This is a special example. Suppose that all the xi are equal to a constant. Then what's the variance? So how do we know it's 0? So if xi is a constant for all I, then the mean of x is just the same as that constant. Right? And the mean of x squared is just equal to that constant squared. Right? Because this sum over a constant value is just m times that constant value, and that cancels out the 1 over m. So the mean of x squared is that constant squared, and then basically this difference then is identically 0. So if there's no variation at all in x, this variance is 0. And now if we introduce fluctuations around some constant value, then we get a non-zero value for the variance. So the variance is measuring the spread in these values x. This is just names. So standard deviation is equal to the square root of the variance. So that's just a part of the lingo that you need to know. All right, what about the covariance? There's another way of doing this. All right, so another way of seeing what the meaning of this expression is to define delta x, which is the deviation of x from the mean. X minus the mean of x. So in this case, what you can show is that the variance can also be expressed as the second moment of delta x. And so that's explicitly showing that it's only the fluctuations around the mean which actually contribute to the variance. Now similarly, one can show the following. So I'm leaving this as an exercise, using those formulas to actually show this, that the correlation of delta x and delta y is equal to the covariance of x and y. So what this quantity is measuring, the covariance is measuring whether or not, so suppose we have fluctuations in x and y, right? So let's say that x and y are both random variables, and right, one example would be x is the temperature of Boston today, and y is the number of people in the swimming pool. All right, that fluctuates over time, but we would expect that if the temperature in Boston is higher than average, then we would expect the number of people in the swimming pool to be higher than average also. So that's a positive covariation. It's a covariation of x and y. They tend to fluctuate up and down together. All right, and some people call that a positive correlation. And then the opposite, if the covariance is negative, that means that x and y tend to fluctuate in opposite directions. Right? So that would be like the temperature in Boston and the number of layers of clothing you're wearing. So that would be an anti-correlated variable. Yep.
What if you have an indoor swimming pool?
If you have an indoor swimming pool? I guess statistics can't cover every possible situation. Thanks, Jen. Well, I don't know. What would it be?
I don't think it would be a...
Okay, it might not fluctuate at all. So suppose that it might not covary at all. Suppose that we have an indoor swimming pool, the number of people in the swimming pool, and the temperature of Boston. In that case, the number of those two variables might fluctuate, but there might not be any correlation whatsoever. Right? So you might end up with, in this case, a zero covariance. So if two variables are independent, if they have nothing to do with each other, then the covariance is 0. All right. Any questions about this? It's a really important quantity because often, one of the basic things about data is you want to know whether two variables are correlated with each other. Do they have anything to do with each other? And if so, what the sign of that correlation is. Okay, so we derived all the stuff, but in the end, yep. Question? Sorry.
Is there a value for like a maximum covariance, or does that cannot be any value? I'm wondering.
Okay, so you're wondering whether the covariance could be, is there any bound on the size of this? So we'll see that in a minute. We'll see that in a minute. All right. Or another way of asking that question is, how do you know when the covariance is large or small? Right. So if we know what the limit is, then we know whether it's large or small. All right, but here's the prescription now. So suppose you want to fit a line to data. Here's the bottom line. If you want to fit a line to data, you take your data points and you compute two statistics. One of them is the covariance, and the other is the variance. And this ratio, right, this ratio will determine the slope of your line. Right? So here's the picture. It's the ratio of the covariance to the variance that determines the slope of this best fit line. And then the intercept, A, you can get by taking this expression right here. So just take once you've got B, then you substitute B into here, and you get this expression for A. So both the slope and the intercept are determined by these statistics. Oh, I should say that these are called second-order statistics because they involve they involve x and y. So the mean of x and the mean of y would be first-order statistics, and these are second-order. Now, before we go on, I want to show you one more way of looking at the problem. Which is the following. Remember, we're trying to make this model fit, right? So what if I go and substitute this expression into here? So then we can express our model fitting problem in this form. In other words, if I just take all of my data, before I do any fitting, I compute the mean of y and the mean of x, and I then subtract the mean of y from all the data points y, and I subtract the mean of x from all the data points x. Then I can do the model fit with a line that goes through the origin. So the resulting A in this particular linear fit is 0. And so all I have to do then is estimate the slope. And the slope then is given by, remember, so this is delta y, and this is delta x.